Let's go JavaScripting! Hi everybody and welcome to another exciting edition of Boring JavaScript. I'm your host, the Virtuoid, aka Mike Smith, and today we're going to be talking about the DataView object. Now, if you remember correctly, 6 weeks ago, I said this. So how do you fix that? Well, let me show you how you fix that. Actually, two different ways to fix it, the hard way and the easy way. So let's go and do the hard way first. And then later, I said this. So I said there are two ways. That was the hard way of doing it. What's the easy way? Well, quite honestly, the easy way is not using type arrays. There is another method that was created just after type arrays were created called DataViews. And DataViews allows you to be able to basically do the same thing here, but to be able to map any of these things, 32 bits, 16 bits, 64 bits, into any position within the buffer. Now, we're not going to cover data views in this video. We're going to cover data views probably that first week of September or something like that. So guess what we're talking about now? Yes, that's correct, the DataView object. You now have the ability to map variables to individual bytes within a data store. Want to see how it works? Let's get started. So in order to show you how the DataView works, we're going to need to have binary data because the DataView allows us to be able to map variables to pieces of data within an array buffer, which is a pure binary array buffer array. That's all there is to it. So this happens to be a database called zoo.data that is a binary database. And it happens to be 4 records within this database. And each of these records represents an animal that happens to be at our zoo. And so what I'm going to do here is I'm going to show you the structure of this zoo data and then start comparing the structure to the pieces of data in the zoo itself to show you how everything works. So let's flip back over to animal here, and this is the data structure for the zoo animals. We start off with a unsigned integer 8-bit unsigned integer as it's called. This will be the type of the animal, 1, 2, 3, or 0. 0 meaning there is no more records. So I can tell you right now I have 4 records and I know my last one happens to be 0, so I should have 3 animals when all is said and done here. But the important thing here is it's going to be an 8-bit unsigned integer. And that basically means it's going to be 1 byte long. Now how do I know it's 1 byte? Because 8 bits equals 1 byte. That's just the way computers have been working since the very dawn of time. Well, at least since the 1940s. The second byte, and let's flip back over to zoo data here, that will represent like this number 1 right here. So my first one happens to be, I know it's for a cat. I think, yeah, this one is going to be right here. That's the next record, happens to be number 2. And I think this one is right here. Yep, that's it right there. That happens to be record number 3. And then this right here happens to be record number 4. So that's so I know where the beginning of the records already are, but as you can see there, the last record happens to be a 0 byte. The second byte, or the second piece of information, is the size of the name. This is the size of the name, basically means the number of characters within the name. That's also going to be an 8-bit unsigned integer. Again, 8 bits, 1 byte, so I know it's 1 byte. So I know that the first one happens to be 6 bytes long, and the second one happens to be 4 bytes long, and the third one happens to be 7 bytes long, right? Oops, right there. So 7 bytes long. So that's the record. That's the entry for the particular size of the name. The next record is the name itself, and that's going to be a variable length, and that's going to be based upon the length that we got from name size, which is the second record. So on zoo data here, 6 bytes happens to be fluffy, so that's one, oops, that's 1, 2, 3, 4, 5, 6. So that's the fluffy record right there. There's fluffy. And then of course we have, you can see in the data here, we have Fido right there, and we have Wiley right here as the other 2. And of course we have zeros for the other ones, which there's no name. Our fourth entry is the weight, and that happens to be a 32-bit floating number. And the floating point number is an IEEE format, 32 bits, which means it's going to be in 4 bytes. Again, how do we know it's 4 bytes? 8 bits per byte, so 32 divided by 8 is 4 bytes. So that would mean that, and I'm just trying to do the quick guess here, that would mean that these 4 bytes for Fluffy happens to, oops, let's try to get that whole number in there. There we go. These 4 bytes right there happens to represent the weight of Fluffy. And I know it looks like a giant number right there, but believe me, IEEE is going to figure it all out for you. No big deal there. And of course, we'll have the same thing for Fido and the same thing for YLE. Animal, the last one here is the age, and that happens to be a 16-bit signed integer. Why signed for an age? Because that means it can go below 0. Only because that's just what I wanted, whatever. So it's a 16-bit integer, and so 16 bits will be 2 bytes. 16 divided by 8 is 2 bytes. So that would mean that the zoo data here, for example, this number right here happens to represent my weight, or excuse me, the age of my cat. And then, of course, have the age of Fido and age of Wiley, which is the coyote. So by using this data structure here and telling DataView how to mimic this particular data structure, we should be able to read all 4 of the records out of this particular database and display the first 3, since the 4th one happens to be a 0, which means end of file. So how do we do that? Well, let's flip back over to our consuming piece of data here, our consuming JavaScript file. And what I mean by the consuming JavaScript file is that it's going to be responsible for actually reading in the file contents and then creating the data view, and then it's going to pass the data view to the animal class to be able to extract everything out. So here is our data view, and it has 3 different arguments, of which the first one is the only one required. The first argument is a pointer to the array buffer, and it must be an array buffer. And this is one of the things you're going to need to be careful about, is that different methods and different functions may produce different data structures that you're not used to. For example, since it has to be an array buffer, if you're doing everything manually, you just create yourself your array buffer, you put your data in there, and you're happy, and everybody can go home. But things like in Node here, where you have the read file sync, that returns its own internal buffer. Buffer is not an array buffer. At least the Node buffer is not an array buffer, so you have to get access to the array buffer. And luckily, Node gives you the ability to get access to the array buffer, or to represent the data as an array buffer, by using the buffer property. So in this case, I'm using the buffer property to point to the array buffer that the data view is going to be contained within. No problem there. The second one is the byte offset. And this will basically say, okay, this data view is going to start not necessarily at this first byte, which is byte number 0, but it may start at 10th byte or 20th byte or the 1000th byte. It doesn't really matter. It just tells you the ability, it gives you the ability to say, I want this data view to start right there. So your data view doesn't have to start at the very beginning. It can start at certain places. In fact, you can have multiple data views to the same array buffer. You can have one starting at 0, one starting at 10, one starting at 20, and 3, 4, 20, 1,000 different ones. Whatever works best for your particular application. And in this case, again, I'm using byte offset from file contents. Why? Because I read the documentation and that's what it told me to do. There we go. The last argument is the length. It doesn't have to be the entire array buffer. Now, if you don't have the, I'm sorry, let me back up there for a second. The second one, which is the byte offset, defaults to 0. If you don't specify it, it will always begin at the very beginning. Just forgot to tell you that. Length here is the number of bytes that will be within the data view. So if you had an array buffer of 100 bytes, your data view may only be from 50 to 55, or 60 to 65, or 40 to 90. Or it could be from 0 to 99. I don't know. It doesn't really matter. So the key here is that you can control where it stops and where it ends. Now, by default, it's just going to go to the very end. So if you're not to have the second or third byte in there, it's going to just do the whole shooting match for you automatically. In this particular case, just for the sake of completeness here, I went ahead and included the byte offset and the length, mostly because I wanted to make absolutely certain that the data I read from read file sync was correct. So that's all there is to the data view. And what that has done here is that's given me my array buffer, and has basically allowed me to get a view of the section of the array buffer to say, okay, these particular bytes represent this number, this particular byte represents this number, this particular byte represents a string, and so on and so forth. And all of that is going to be done within the animal class. So now let's take a look at the animal class and show you where the real magic begins. So here we go. Here's the animal class. There's a lot here. All right, so basically what I've done here is that the data view gives a lot of helper methods to be able to extract numbers. Things like a signed 8-bit signed integer, an 8-bit unsigned integer, 16-bit signed integer, 16-bit unsigned integer, a 32-bit signed integer, 32-bit unsigned integer, a 32-bit IEEE number, a 64-bit unsigned integer, and so on and so forth. All those different numbers are available to you as methods within the data view. So our job here is to be able to say, okay, I want byte number, let's say 5 here, to represent a particular single unsigned 8-bit unsigned binary number. And so DataView will say, okay, once I do that, then I'm going to represent this particular data byte with a particular variable. And that's what we're doing at the very beginning here. Now remember, let's go back to our data type. The very first byte is an 8-bit unsigned integer. So how do I get that as extracted? I give it the 8-bit unsigned integer method, which is get uint8. Now, the key here is, and the most important thing is, you've got to tell it where to actually start reading it. Now it already knows how many bytes it needs to read, because an 8-bit integer is 1 byte. So you've got to tell it where to start within the array, or within data view, where that piece of data must start. And in this case, we're going to start at offset. And offset happens to be the very beginning of the data stream we're going to take a look at. Now, again, our data view is going to have 4 records in it. So our offset, as we pass into the constructor here, as we're passing in both the data view and the offset, our offset is going to basically say, I want to start at this part of the record I want to start at this part of the data view to get record. Then I want to start at this part. Then I want to start at this part. Then I want to start at this part. And that will allow me to be able to grab the correct record out of the data view. Excuse me. So we get the 8-bit unsigned integer there for type, and then I assign this type to either cat, dog, coyote, or blank, just because I want to. I want to have it as a string there. The second byte happens to be the number of bytes in the string, and I'm getting that from right here. Again, I'm doing the get unsigned integer 8, which is the 8-bit unsigned integer, but the offset is going to be offset plus 1. Why plus 1? Because 1 byte is, we've already read in 1 byte, so the second byte is going to be the name length, so it's going to be the offset plus 1. Because we've already done 1 byte, that's why we have the plus 1. That gets me the name length. The next thing here is I get the name by giving it the offset of 2, because we've already done 2 bytes so far, 2 uint8s, which are 2 8-bit numbers. That's 2 bytes. So we get the offset plus 2 plus the name length. Now, there is no method within DataView to be able to give you a string, so I had to write my own down here for getName, which basically does this real long piece of stuff right here. That basically does a slice of the buffer, turns it into a uint array, and then applies that to the from character code method, and all of that will basically convert an entire array of single bytes into a string. That's all it really does. It looks complicated, but it's not really complicated. But because there's so much there, that's why I just went ahead and made it into a little function to make it a little nice, fun, and easy. So I get the name, which again starts at the offset plus 2, because I've already done the 2 bytes. And we're going to pass it also the length of the number of bytes within the name. Next is the weight, which is a 4-bit floating point number. To get that, that's going to be get float 32. Ooh, that works out really nice. Where's the offset start? The offset starts at offset, which is the beginning of the view, the section of the view I want to take a look at, plus 2, which represents the 2 unsigned 8-bit integers at the very beginning, and the name length, which represents the length of the name. So that will give me the offset of where to start looking for weight. And it will automatically do 4 bytes, because a 32-bit floating point number will always take up 4 bytes. There is an extra argument here that you don't find on the getInt8s, and that's called the little Indian, big Indian flag. And this tells you whether to be able to interpret this number in big Indian format or little Indian format. I'm not going to get into the difference between the two of them here right now. I'm actually going to do a little bit on that at the very end of this video here to kind of show you what we mean by little Indian, big Indian. For right now, this particular thing works as little Indian. We'll show you that here in just a second. So that gets my floating point number, and that goes into weight, and then into age. It's an integer 16, so I get integer 16, which is a 2-bit number, 2-byte number, and I'm going to pass it the offset plus 6, why 6? 2 bytes for the 2 uint8s at the very beginning, 4 bytes for the floating point number, plus the name length, which is the length of the name, so that will give me pointed to the age, and then I'm going to also interpret it in little Indian format. And that's it. That takes care of now of our type, our size of the name, the weight, and the age, and that will allow me to give back a type, cat, dog, coyote, or blank, a name, whatever the name is, the weight, and the age. So let's flip back over to our consuming. We get our first new animal starting at offset 0, because that's what offset is. And then while animal type does not equal blank, because animal type is going to come back as blank if that's the end of the file, I'm just going to do a simple console.log. I'm going to set my offset to the next piece of data available. So to be able to help my program for that, I've created a size property by using a getter function. And that size property down here returns to me the exact byte size of this record. There's our uint8. Our uint8 plus the name, the length of the name of the animal, our floating point 32-bit size 1, and our 16-bit size integer. So adding all of those together will give me the exact byte size of the record as it appears inside the data stream. So that allows me to be able to have offset come in at the new number to where it expects to have that next record. And then I just need to read in the next record, and once it's finished, and everything is done. Whew. You want to see how it works? Okay, now that we're in Node, let's type in Node DataView. And there we are. There's our name, there's our type, there's our weight, there's our age. And there's the 3 records. Remember I said there are 4 records in there, but the last record had a 0 point. So those are 3 records. So this shows you how easy it is to be able to map a set of data to a particular binary operation. Now, we have I did a sample one here. What about in real life? How's this going to work in real life? Now, if you remember from 6 weeks ago when I did the type arrays, I showed you how to do it with a zip file. Well, I'm going to show you how to do the data view with the zip file now. So let's take a look at it. So now you've been given a zip file to be able to use DataView to extract the information from. How are you going to do that? Well, first of all, let's take a look at the zip file itself. And I have that up on the screen right here. And the zip file is basically split into 2 sections. The first section explains or lists out all the different files and the contents of those files themselves, which you see all up through here. The second section, which is down toward the bottom here, will also give you the same files, but all the different directories that they are listed into. Because as you know, with the zip file, you can have the files into different directories. Now, I'm not going to worry about the directory section. All I'm going to worry about is just the files that are in there. So I'm going to worry about the top part here. Now, in the top part, we have, in this particular case, 4 different files in this zip file here, but each one of these follows a specific format. Just like the zoo example did, each one of these, I can be able to get a description of the files and be able to extract all the data based upon that description. For example, I can tell you right now I've got blank.html right there. There's one of my files. Here's classlist.css. There's another one of the files. Here's classlist.html. There's the 3rd file, and there's a 4th one in here somewhere. Yep, there it is right there. Classlist.js. So that happens to be a 4th file available to me. So all that information there is the actual compressed data for those particular files. So how do we extract the files? Well, the first thing we need to do is to figure out what each of the different bytes means. Just like we did in the zoo example, we got to figure out what all this stuff really means. So let's go over to the file entry. And there it is. I got this straight from the zip documentation online. Just Google it. You can find it. It's no big deal. So this tells me everything I need to know. Each file starts off with a particular signature. If that signature is not there, there's no more file. And I'm going to be using that to be able to figure out when my listing is stopped. Because the first thing it's going to have, it'll be this particular zip file. And then once I get past the last file, the next signature will be the directory signature. So I'm going to stop at that point. Different versions, purpose bit files, compression method, la-di-da-di-da-di-da. Here's the compressed size. I'll be using that in my report. And then finally we get down to the file name itself. And this is going to be a variable size. And we get the file size from this particular entry right there. And this entry right here will tell us the file size. We have an extra file field length there, which will give us some extra fields. I don't know exactly what that is. In my case, all of them come out to be 0, so it doesn't really matter. After all of this happens to be the header information, but after all of this, you have the actual physical data itself. So we're going to need to have a way to be able to not only get the header information, but the actual data. Now, how are we going to be able to do that? Well, it's very, very simple here, is that we have the compressed size right there, and that tells me how many bytes are within the compressed size. I will be using that compressed size plus all of this data right here, plus all this data right here to be able to figure out the exact size of the data that is within the array buffer. And that will allow me to then advance through the data or through the array buffer as we go along here to be able to go from the first record to the second record to the third record and so on and so forth. So how are we doing that within the file entry here? Very, very simple. I am constructing the data view within the buffer itself. In this case, I want to have a data view associated with each of the different records so I can then manipulate it at a later point in time. Because remember I said you could have multiple data views per array buffer, so I'm going to have this big array buffer coming in that I've read in from the file, and I'm just going to have a data view for each one of the records. I didn't have to do that. I could have had one data view for the whole thing, but in this case, I just wanted to have a data view for each record. There's my start. Here is where I get all the signatures, and it's extraordinarily simple. The get it 32s, get it 16s, the blah, 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 and so on and so forth. All of them with the little Indian flag set to true. And again, I will cover all that in my next section here. The important thing for me here is the compressed size and the file name length and the extra field length. Because once I read in the header, I then have to sit there and read in the file name. And I'm using the exact same process that I did here with the zoo, is that I'm going to get the slice of the buffer and apply it to the from character code to be able to get to the string. In each one of these cases, I'm still sitting here and getting the, and setting the offset, to where, making sure that I've set this offset correctly to know where I'm starting at the same place. So there's where I reset the offset. I've got the header length. I basically reset the offset to get the extra field, got the extra field. Here's the file data itself. This gets me the physical data within the buffer that I am saving, and I'm saving it as the size of the compressed size there. Here is the file offset, and this file offset basically is my final calculation on physically how big within the data structure, or within this record structure, the number of bytes it's taken. And that basically is the file offset plus 30 bytes plus the header's file length plus the extra file length plus the compressed size. Once I got all of that, that means that file offset will be exactly the size of all the data that within that record. So that when I get to that next record, I can just advance my pointer to the second record, and it'll be up and running and ready to go. And then past that, I just got a couple of functions here, like is file header. This is where I test to find out it's a file header. Actually, I don't use that because I already know it's a file header. But I do use this, is central directory structure, because once I get the marker for a central directory structure, I know at that point I'm out of the files and I'm into the directory structure section of the zip file, and we can stop the whole process there. So I'm using this as my stop point. And then this just allows me to get the 32-bit integer from over here. So yeah, it's no big deal there. So that's all there is to it. Here's the header, the file names, the extra fields, all the data. That's all there is to it. So my zip file, which is my consuming file, is real simple, and it looks exactly the same as the file that we used for the zoo earlier. I greeted my zip file. I've got a little loop for while all done. Again, like I said, I'm using is central directory structure as my stopping point. Earlier, I'd used the 0 record as my stopping point. Now I'm using is central directory structure as my stopping point. Once I'm done, I'm all done. Otherwise, I push the new file entry into files. So once it gets down to here, files contains everything that I have, or all the different files that I have within the zip file. And then I'm just going to print out the compressed size and the file name. Want to see how it works? Let's get to it. Let's get over to zip. Get over to node. Type in node zip. Yep, 4 files found: blank, class, list, CSS, HTML, and JS. So that shows you how you are able to use the data view within a real-world environment to be able to read real-world binary databases, which is basically all a zip file is. Now, let's flip back over to the code. And earlier, I told you that I will show you what this little Indian true thing means, or the second argument to a lot of these pieces of information means, and that's going to be next. So what is this little endian and big endian, which is spelled, by the way, L-I-T-T-L-E space E-N-D-I-A-N and B-I-G space E-N-D-I-A-N? What do those two mean? It's all about most and least significant bytes. So to give you the example here, we're going to be using our unsigned integer 16-bit, for example. And an unsigned integer 16-bit gives me a number between 0 and 65,535. To represent that number, we have 2 bytes. So for example, let's say our number is 258. Now that's going to be 2 bytes of information. And whenever you have 2 bytes of information on your unsigned integer, you always take the most significant byte and multiply it by 256, then add in the least significant byte. So again, most significant byte times 256, add in the least significant byte. So for 258, our most significant byte is going to be the number 1, and our least significant byte is going to be the number 2, because 1 times 256 is 256, add 2 is 258. And that's real simple. So here's the problem. You've got your data stream going in, and you suddenly reach that 01 and 02 number in there. You think, okay, well, yeah, we just read those in, there's 256. Well, are you, 258, excuse me. Well, are you sure? Well, you're not really sure, and that's the problem. What if it happens to be flipped over? What if it happens to be that number 1 happens to be the least significant number, and the number 2 happens to be the most significant? Well, then your number is 513, because 2 times 256, the most significant number, is 512, plus 1 is 513. So, but you know that can't be right. So that's where big endian and little endian comes into play, is that if you know your number happens to be big endian, that means that your number's most significant byte will be the first byte that you encounter, and the least significant byte will be the second byte that you encounter. So in our example here, as we're going through here and we hit that 0102, and we're reading in big endian, we know that the 01 is our most significant byte. We multiply that by 256, add in the second byte, we get 258. Now, if we're reading in as little endian, and we're doing our data stream there, then our number is going to have to be a 2 and then a 1, flipped over, because 2 is going to be our least significant number and 1 will be our most significant. So that's the key here. As you're reading through your data stream, big endian, the most significant byte is first, little endian, the least significant byte is first. And that's critically important as you're going through as you're reading in the data from using the data view here. You've got to know whether all the data that you're reading in that is 16 or 32 bits long or 64 bits long is in little endian or big endian format. So for example, here in my animal class here, I've got both my weight and my age in what we call little endian format. By default, all of these get 32s and get 16s and all the different variations of them, the endian format is set to false by default. So it's set to big endian by default. To be able to set it to little endian, I've got to set this value to true. Now, why do I not have it here in the 8? Because with an 8-bit value, it's only 1 byte. There is no such a thing as most significant byte and least significant byte. There's no such a thing. So you'll never get that. But with the 32s and the 16s and the 64s also, since you can do that in JavaScript, you always got to be able to tell it whether it's in big endian or little endian format. And it makes a giant difference. And let me show you why I mean by that. Let's flip back over to Node and let's take a look at our cat data. This is the cat data from the zoo. Notice that the age is 4, and we read that in with a signed integer 16-bit. So I had to use little endian there to set it for true, and the age came out to be 4, which is correct. Let's flip back over to our code and let's take a look at our raw data. And here is our raw data for Fluffy. There is the type, there is the length of the file name. So it's 1, 2, 3, 4, 5, 6. Here's the 4-byte floating point number. So this 0400 is our 2-byte 16-bit number here. So I've highlighted 04 here. And on the cheat sheet on the right-hand side here, the word, which is a 2-byte number, comes out to be 1024. Well, that's wrong. So what happened here? Well, what's happened here is that by default, also this particular program I'm using uses big endian format. If you look down at the very bottom here, I hope you can see my cursor down there. I'm kind of circling right now. We have BE and little e, and this stands for big endian and little endian. So I'm telling my program here to be able to interpret this in big endian format. If I flip it over to little endian, aha, the number comes up to be 4 perfectly. So that's the reason that it's extremely important to do big endian and little endian. And in fact, as you get the much larger numbers, the 32-bit numbers, for example, it could get even worse. So for example, let's flip back over to Node. The age of my cat is 41.737, so on and so forth. So if we go back over to here, D9 at the top here starts off my floating point number. So if I highlight D9, It's saying that the floating point is negative 8.519E15, which is completely, totally wrong. Badly wrong. So the reason it's wrong is that it's still in big Indian format, but that's not how I want to read it in. I want to read it in little Indian format. So click on little Indian. Sure enough, we get 41.737156 and so on and so forth. So it's extremely important to be able to know ahead of time whether your 16 and 32 and 64-bit data is stored in little Indian or big Indian format, because if you don't, it will blow up. Now, why is it called big Indian and little Indian? Well, that is actually a very cute little story. I didn't find that out until I started researching this particular thing. It all has to do with an egg. Well, that flipped over on the right-hand side incorrectly, but that didn't really work very well. Let's see if we can get that egg to look a little bit better. Hold on one second here. There we go. I had to expand the size of my monitor here to make sure that the egg came out correctly, because the egg came out squished. So this is the egg. It's all based upon an egg and the story Gulliver's Travels, which was written by Jonathan Swift. Now, when Gulliver went to the Lilliputans, he noticed that the Lilliputans were had split their society based upon how they cracked their hard-boiled eggs. Some of them would crack their hard-boiled eggs on the little end, E-N-D. Some of them would start cracking them on the big end, the big E-N-D. And the Lilliputian society was split up between the big end Indians and the little Indians. And so the person who created this particular format said, I like Gulliver's Travels. This is a good explanation for it. So let's call this Little Indian and Big Indian. So you can think about it is that if you're doing Big Indian, you're cracking your data with the big end first, or the most significant byte. If you're doing Little Indian, you're cracking your data with the little end first, or the least significant byte first. So that is the reason they're called Big Indian and Little Indian. And that's all there is to the DataView object. I hope you enjoyed our video. Hope it didn't bore you to death. Please see all of our videos at www.boringjavascript.com. Subscribe to our YouTube channel, or check out everything we have at www.thevirtuoid.com. Thanks again for watching, and we'll see you later.